Yes. All right. Great. Okay, here we go. Thank you for those connecting. We are starting another Meet the Scientist session. If you're new to Meet the Scientist, it is a program that is part of the Arctic and Earth Science activities happening at University of Alaska Fairbanks. I'm Bonnie Murray. I'm coming to you from NASA Langley Research Center. Today, the scientist that you'll be meeting is Kelly Brunt. And Kelly's up there at Goddard Space Flight Center. Hi, Kelly.
How's it going?
We're doing great. Happy to see you there at Goddard. Kelly is an expert in analyzing ice sheets. She's a researcher at Goddard Space Flight Center, and she is headed out next week to Antarctica to do some verification and some calibration that will allow us to make sure that the ICESat 2 measurements are accurate. So we'll get back and let you tell us all about that in just a minute, Kelly.
Perfect.
I want to tell you a little more about that. So Kelly's going to be sharing with us how the ICESat satellite is working. How does it collect its measurements? When did it launch? What is the mission all about? Kelly's also going to be sharing information about IceBridge. IceBridge is an airborne campaign, so data collected from the airplane, and she'll be sharing information about how that works. So another level of data collection. And then finally, she'll be sharing information about the ground campaign, ground-based measurement that Kelly did in the past. And you probably watched that video. That's the video that I sent out along with this, and Kelly will be showing some clips of that during her presentation as well. So those ground-based measurements are very important also. I mentioned that this is part of Arctic and Earth Science, and that is funded through NASA's Science Mission Directorate. So if you go on and you Google Arctic and Earth Science, you'll find that. I'll share that a little later in the broadcast as well. But it's a program where teachers receive training in global learning and observations to benefit the environment. So the teachers receive training on the protocols, a very specific way to collect data. Why a specific way? Because if we all collect data the same way, then we can compare those measurements and verify and compare our calculations, knowing that they were gathered in a similar manner. So those protocols are what are studied. The teachers study that during a week-long training, and then they bring that back to their classes. So right now we have one class connected with us, Mr. Stanik's class in Shishmaref, Alaska, and we'll say hello. Hello to all of you. Yes, and we will have, I do want to say before we even start talking with Shishmaref, we will have other classes joining us in about 10 minutes or so, and I'll do another short introduction with those classes as well. Shishmaref has to leave. They're volleyball champions, and some of them have to leave partway through the broadcast, so we're getting an early start with them to give them time to talk to Kelly. So let's start by asking all of you, tell us a little bit about Shishmaref. Where is it in Alaska? What's it like there right now? Those kind of things. So who wants to start? I can pick on people. I would never pick on people. I can select volunteers, or you can volunteer yourselves. Where is Shishmaref in relation to the state of Alaska?
Where's Shishmaref? Somebody.
Anyone? All right, how about the gentleman sitting right in the center with a blue t-shirt? Tell us your name and tell us where is Shishmaref, at the northern part, the west, the east? Is it near the water? Is it inland? Where is Shishmaref?
My name is Brian.
And where is Shishmaref?
It's in the Seward Peninsula.
Okay, perfect. Thank you. Thank you. So the young lady sitting right to the left there with the kind of rose-colored sweatshirt on, what's the weather like there now? What's it like in Shishmaref right now today?
What's your name first?
Tell us your name.
Say it loud again.
Charla.
Hi, Charla. What's the weather like there today?
Oh, breezy, huh?
Cold.
Okay, so cold's a relative word, right? Cold, I think it's cold here today. I wore my scarf and my sweater, and it's 47. Is that what you mean by cold?
Yep.
No,
No.
it's not 40.
Trick question. So what's cold? Anybody else?
How cold is it today?
It's like 15 degrees.
Okay. Yeah, that's a little colder than we get. I don't even think we get to 15 degrees here, honestly. It would be really rare. Once in a while, we may get that low, but it really doesn't even get that cold here. So that's interesting. Very different. Yeah. All right. Well, I
And the
want to
air-
introduce. Say it again.
The air's too. I was gonna say the air is kind of damp, so it's kind of chilling. I mean,
Oh.
even more so than 15 degrees.
Right. So I want to let you talk to Kelly because ICESat is measuring changes in sea ice, and you all experience sea ice where you are, correct?
Yes. Yep.
Yeah. I understand you can actually see Russia from Shishmaref sometimes. Is that true?
From the air.
Okay. Like as you're flying, yeah. So just to give people a perception of where you are. So have you noticed changes in sea ice since you've lived in Shishmaref? You know, in your lifetime, have you noticed changes? Yeah. Okay, changes, is it an increase or a decrease?
Foolishness.
Oh.
What kind of changes you guys seen? Ice is breaking up earlier. What else you guys see? The ocean should be frozen by now, yeah.
Ah,
But it's just
Okay.
getting slushy, right?
so Kelly, I'm switching over to you as you're hearing their account, and if you want to, talk a little bit about what you're hearing them tell you and how that fits in with what you're measuring.
Yeah, so we'll have some slides later. Hopefully you guys will be able to see all of them. We'll try to work to make sure that happens for you. But basically, I'm part of a mission called ICESat 2, and it's a satellite laser altimeter. What does that mean? It means we're just basically shooting light or laser from the satellite, letting it bounce off the surface, come back to the satellite. We use a two-way travel time of light to then precisely and accurately assess the elevation of the ground below us, ground or sea ice or even ocean. When we make a repeated measurement, we can actually get at the change. Sea ice is a little unique. We can measure not just the height, but then with buoyancy arguments, we can look at thickness. And I'll show you how we've already started to monitor how our sea ice is changing through time. So you'll see a great animation that basically totally confirms or validates or verifies exactly what you guys are saying. So that's pretty interesting. Just to let you guys know, I lived in Anchorage for a number of years, so I'm really actually excited to be talking to a school in Alaska. I realize that Anchorage is only the closest city to Alaska. It's very out of touch with the rest of the state, but I am super excited to be able to talk to you guys. I know that you guys haven't seen any lead-in material, or I know you guys maybe watched a video or so beforehand, but does anyone have any questions to sort of start a conversation between us before we show the video a little bit later? Is there anything you guys want to know in advance of this? Or do we have to pick on Edward? Should we?
We are picking on Edward. But yeah, so you did watch the video. Do you have any questions from that? And I have questions for you if not, but I want to let you, if there's anything on your mind first, talk about that. Did any questions come to mind as you watched the video of the work Kelly's doing?
We actually didn't get to watch the video with this group.
Oh, I'm sorry. I was assuming. Okay, well, that is a little different then. Say it again?
We just kind of talked about that we were going to meet Kelly and kind of that the satellite takes data regarding ice. So that's about their knowledge. But
Okay, great.
I mean, some of these boys have been on the ice hunting, and so they got a decent knowledge of sea ice, and so maybe they can talk about that.
Right. So that was going to be my question to you. I said I had questions too. So I don't have experience with sea ice other than I went up to Barrow and saw sea ice in June. I was there when it was just starting to break up. But tell me about sea ice a little bit. You have the experiences with this. What activities do you do on the sea ice? And it doesn't have to be you, Edward. We can go to the back of the room. Edward, you've been very helpful so far. How about there are two gentlemen sitting to the run with his arm right on the table there. Tell us your name and have you had any experiences going out on the ice?
Hi, my name is Shane, and the activities we do on the ice is seal hunting.
Okay. Seal hunting.
Yeah, and ice fishing.
Okay. So have you talked to those, maybe your grandparents, or even your parents, and have they shared any stories about how the ice was different maybe 10, 15 years ago? Anything?
Yeah.
Yep.
Can you share them with us? How was the ice different 10 or 15 years ago?
It was thicker.
Freeze quickly.
Yeah. So not just more of it, but actually thicker ice. Yeah.
Yep.
Mhm. So Kelly, that kind of lines up with what you're finding, correct?
Lines-
I know you're going to
lines up
show
really
that
well.
later.
Yeah, that's fantastic. It's a great lead into a slide that you guys will see later for sure. That's great. Not great for the ice.
Yeah.
That's not what I mean.
Yeah. Yeah.
One of the things that's lately when the hunters are out on the ice, in the spring, they're taking chances with their lives.
Yeah.
More so. We had 3 snow machines go through ice last year.
Yeah.
The rigs were saved and the people were saved, but we even had one of our current seniors. They almost lost their boat because of weather conditions and whatnot. So,
Right. Yeah. So it's not just a matter of how is this affecting the climate and how is this affecting, air currents around the globe. This is affecting livelihoods and possibly affecting lives. We need to think about those things. Yeah, I don't experience that, and so I appreciate you sharing that with me. Thank you. Really appreciate that. All right. I see we have some other schools that joined. Let me start welcoming them in. Let's see who we've got there. I recognize Mr. Fontes, is that right?
Yes.
Yes.
Good morning.
All right, there we are. So that would be Chinook Montessori School, is that right?
Yes, that's right.
Okay, great. And you are near Fairbanks, is that correct?
We're actually in Fairbanks.
Okay, so let me ask some of the students, what's around you? Are there mountains around you? Does anybody want to answer, or is it flat? Okay, tell us your name.
My name is Trenton, and yes, there are many mountains around Fairbanks.
Okay, awesome. How about what's growing there? Can someone else answer that? Is it pretty desolate with not much growing, or are there a lot of trees? What's growing? Okay, tell me your name. Right there in the blue sweater with flowers.
There's a bunch of plants like trees and other plants. My name is Adlin. There's a bunch of plants growing, like a bunch of trees and other plants.
Okay, great. Thank you. Thank you very much. And I see Miss West class coming in now. Is that right?
That's
There
right.
she is. All right, great. Welcome. Thank you. Okay, let's go over to, let's see, I think that's Miss Trezino's class. Is that right? That would be Crawford Elementary? All
Yeah,
right.
we're at Crawford. Hi.
Hello, Crawford Elementary. Welcome. Okay, so let's ask you the same questions. Where in Alaska is Crawford? And one of the students, how about bright green sweatshirt right in the front there? Tell me your name.
My name's Cameron, and we live on Eielson Air Force.
I couldn't hear it. Just say it again, louder.
Louder.
My name's Cameron, and we live on Eielson Air Force Base.
Okay, Eielson Air Force Base. Thank you. All right, so someone in the back stood up and volunteered. If you could walk up to the front, I'd like to know what the weather's like there today. What kind of weather are you having these days?
Go ahead. Go ahead, Adrian. Say your name.
I'm Adrian, and it's really cold. It's like 6 degrees right now, and it's
6?
it
Like,
is-
okay, 6, like just a single digit 6?
yes.
Whew. That is really cold, Adrian. That is, so I'm here in, let me go back to me. All right, so I'm here at NASA Langley Research Center, and I thought it was cold today. I wore my sweater and a scarf, but it's actually 45 degrees, so I guess I can't complain about it being cold, huh? Not really cold here. So you'll see we also have Shishmaref connected. You heard them talking when we started, and we're actually expecting one more school. I know they couldn't join until right at 2, and that's Mount Scott Learning Center. So they'll be joining in just a few minutes. I want to welcome you all and just briefly remind you all that this is one of the Meet the Scientist sessions. So the scientist you will meet today is Kelly Brunt. There she is. And she is up at Goddard Space Flight Center, and that is in Maryland. So we were talking earlier that I am at the bottom of the Chesapeake Bay over on the East Coast, and Kelly's up at the top of the Chesapeake Bay. Both of us here on the East Coast, down in the lower 48. All right. And I think that is Mount Scott Learning Center joining us. I think some of the students are still coming in, but we'll say hello to you. Hello at Mount Scott. Thanks for waving back. Awesome.
Hey, all right, guys, wave.
There we go. All right. So I hear Miss Picone up there, and Mr. Lindquist's class is going to be with us as well, correct?
You know what? It's just our combined classes, so it's just going to
Gotcha.
be me.
Perfect. Okay, that's great. Thanks for letting me know. So someone tell me, where is Mount Scott Learning Center?
Somewhere like this.
Tell me your name first. Who would like to volunteer?
Well, my name is Mariah.
I can't, you're not on camera. Can you walk over to the camera? Oh, wait, I'm sorry. You are. Just talk louder. You're fine. Just talk louder. Yeah.
My name's Mariah. Nice to meet you. We're located in Portland, Oregon. The climate here is pretty rainy most of the time, especially during this time of year. Right now, it's about 58 degrees Fahrenheit. So, yeah.
Okay, so 58. Yeah, that's more like my kind of temperatures, Mariah. I don't know if you were on when I said it's 45 here today in Hampton. Thank you. Thank you. So I want to go back over to Kelly's slide for a second, and I want to talk about Kelly and let you get her name down. Now, there's a lot of us connected, so it's kind of cutting off Kelly's last name. But I'll tell you, it's B-R-U-N-T, because I want you to make a note of that on your Foursquare notes. So Kelly Brunt is connected with us. She is a research scientist at NASA Goddard Space Flight Center. We already told you that's up in Maryland. And she has developed expertise in analyzing ice sheets. So she's an ice expert, and she'll tell you a little bit more about that when she gets started. Right now, she's working on the ICESat 2 satellite, working on that program. And specifically, Kelly's activities are focused on validation and calibration of the satellite. And so you might want to add those words down in your Foursquare notes as well, because we're going to ask you later, warning, quiz at the end, what does it mean to be calibrating and verifying data from a satellite? And how can you be involved in that? We're going to cover that at the end as well. So I think that's everything. Excuse me. I'm not sure if I said thank you to NASA Science Mission Directorate, but I want to do that because they provide funding for this program. So Kelly, while I get my voice back,
I got you.
Start your presentation.
How's it going? Hey, I'm really excited to be talking to all you folks in Alaska. We've got a short presentation to go through. We'll try to crank through it so that some of the classes that have to take off can see most of the slides. So if we'll start the presentation. So just really quickly, I think you guys got my name off the last slide, but there it is again in case it was obscured. At the very bottom is a Twitter handle at Kelly M. Brunt. And you can actually follow that, follow along in some of our activities. We're going to be going to Antarctica coming up. In fact, I leave in about a week. And I'll be posting photos from down there, which could be fun to follow. So I was asked to sort of present a slide on what I do and actually why I do it. So I'm a glaciologist. I study glaciers. That's my specialty. And I do that, I study mostly the ice sheets, the really big masses of ice. And I do that with satellite data because they're at a scale that really requires satellite look. You know, continent scales require satellites to actually get a good sense of what's going on. And that's what brought me to NASA. But why the heck do I study ice? Basically, I grew up in Connecticut and I skied. That's what our family did. That's how we hung out together. Skiing was a really important part of that. And I think that's probably where I got the sort of drive to go into studying ice and earth sciences. So I did an undergrad, a bachelor's degree at Syracuse in geology. That's number 2 with the star and the skier. I ski raced for them. That was fun. I did a master's degree at the University of Montana. More skiing. That was great. Took me too long to finish that degree because the skiing got better. Here's the next one. Bullet number 4 is the most important one. I worked for the USGS for 3 years in Anchorage, and that gave me great exposure to a lot of Alaska. But I started doing remote sensing there. That got me back into sort of working with ice sheets again. So I started working for the U.S. Antarctic program. That took me to Antarctica for the first time. While I was there, I got really interested in going back to school, and I did. I went back to school at the University of Chicago, got a degree in glaciology. Not a lot of skiing in Chicago. That's a sad star without a skier next to it. I ended up doing a little bit of what we call postdoctoral work at the University of California in San Diego, or Scripps Institute of Oceanography. Again, another sad star without a skier next to it. And then ultimately that brought me to NASA, where I am now at the top of the Chesapeake. So that's sort of how I got involved in this. It starts with skiing and sort of, evolves into this love of ice, which is great. So let's talk about our ice sheets and the health of our ice sheets. I think we have one school, the one in Oregon. Could you mute your monitor for right now? At the end of this, we'll come back to questions and whatnot, but we're getting some feedback. So ultimately, what's going on here? In Greenland, you can see from the graph that we're showing, basically our ice sheets are losing mass. And we know this from a couple different data sets. Ultimately, what you see in there is some spikiness, what we call that sort of interannual variability, but the overall trend is down. It's kind of unequivocal. Basically, at the start of the time series, at the end of the time series is a big difference. We're losing a lot of mass in Greenland. We've got a similar story, although not as dramatic, in Antarctica. Again, you see some spikiness, some more interannual variability, but the overall trend is down. We're definitely losing mass. And in both these animations, you can see that those places that we're losing mass the most are around the fringe of Antarctica, where our ice sheets are in contact with both our warming atmosphere and our warming oceans. When we take that ice mass and we melt it, we put it right into the oceans, and that contributes directly to mean sea level rise. So there's a societal impact on those changes, and that's important. Let's go to sea ice. And the folks that I was talking to before we really got rolling, we're talking about a decline in sea ice and a decline in the thickness. This is a wicked cool animation that's not just showing you the change in the extent through time, but it's also showing you the change in thickness. The really white parts of the animation are older and thicker. Those two things go together, are older and thicker sea ice. And what you're going to take from comparing the beginning of this animation to comparing it to the last frame of the animation is the amount of old, thick ice is declining. It's exactly what the students up on the Seward Peninsula were telling us, that what they're actually observing on a daily basis is the change in their sea ice having a direct impact on the way that they're living, again, off the Seward Peninsula, because I cannot remember the name of the town. I apologize.
I'll help you with that. I can help you with that. It's Shishmaref.
Perfect. So this is really important. Now, changes in our sea ice, while that doesn't contribute directly to mean sea level, so it has a different societal impact, basically changes in our sea ice change the way that the heat flux, but the exchange between the ocean and the atmosphere takes place. When we change that flux, when we change our sea ice and we change that flux, that has an impact on global weather patterns. So whereas changes in our ice sheets has a direct impact on the people on the coast, changes in our sea ice has an impact on the entire community, even those, in central Iowa. So this is the last frame. I don't expect you to remember the first frame, but here it is. So I'm comparing September of, we already discussed this, was it 94, to September of 2016 or thereabouts. The text is really small, I'm sorry. But the point is this is September to September, and it's pretty obvious that that thick, old ice is really broken down, and you cannot make 5-year-old sea ice in 1 calendar year. So between the losses of our ice sheets and the changing thickness of our sea ice, you can imagine that there was an absolute societal need for a mission like ICESat 2 that is precisely and accurately measuring changes in our polar regions. We just launched that satellite. We launched it September 15th. And the next video shows the launch. We're going to play just a little bit of it. Oh, sorry, this is the overview of the ICESat 2 mission. So this will get you kind of in line with what we're doing.
Thanks for starting that over, Shane.
From satellite data, we have a very good handle of how our Earth looks like. We can see oceans, we can see the sea ice, we can see our forest. What is much, much harder to measure is how high things are on a global scale. Almost impossible.
ICESat 2 adds the third dimension, the elevation. Repeating measurements from ICESat 2 will allow us to measure changes in the ice sheets or in the ocean or in land.
ICESat 2 is designed to measure the changes that are going on in the cryosphere, in the polar regions.
All the change is at the edges. Those are the steeply sloping parts of the glacier that interact with the ocean, and that's where all the action is. That's where all the mass is being lost.
In order to estimate the mass changes, we need to know the height of things. The mission ICESat 2 carries a single instrument. It's called ATLAS, the Advanced Topographic Laser Altimeter System.
ATLAS sends out small pulses of laser light 10,000 times a second. And by measuring precisely how long it takes that light to go from the spacecraft down to the Earth and back up to the spacecraft, allows us to figure out what the height of the surface is beneath ICESat 2.
We need to measure the time of flight of a single photon or a single laser pulse with a precision of a billionth of a second.
NASA engineers had to come up with entirely new ways of measuring time very precisely.
A billionth of a second translates to an elevation change precision of just a few centimeters. Climate change is amplified in the polar regions. ICESat 2 is designed to measure those areas and will help us to understand what's going on with our planet.
Good. So with that sort of background information, then the next thing we'll point out is that we launched September 15th, about a month and a half ago or so, and it was super exciting. I'm going to show you the launch, part of the launch video. We'll cut it off a little bit short. But here's the launch. This is very exciting, although it was 6 in the morning. There's no audio? Yeah. Perfect. So basically, there's no audio, but ultimately, that's okay because all that the audio was what we do best at NASA, which is counting backwards from 10. Very exciting launch. Again, early in the morning. The rocket goes into the marine layer, and then in a second or two, it comes out. But I can't tell you, it was both exciting and stressful. Very, very busy morning out at the launch site. So at this point, the rocket itself was inside what we call a marine layer, or the fog that comes in usually in the mornings, associated with very coastal Pacific Ocean in this case. And then it came back out, and ultimately we were unbelievably happy with the results there. We're just now starting to get a sense of what the data are looking like, and we're pretty happy overall. All the models that we put together beforehand seem to be accurate, which is great. In the upper left, you're seeing ICESat-2 signal return over ice sheet. The lower left has ICESat-2 signal return over sea ice. Those red arrows in there are pointing to areas that we call leads, or where the sea ice separates a little bit and you have actual access to the open water. The seals tend to like that type of environment. And on the right, that whole panel is associated with vegetation. And with ICESat-2, we're able to see what we call the crown of the trees and the ground beneath. And that's pretty important for our vegetation researchers. So we're not going to watch this whole video evolve, but this is basically giving you a mock-up of a day in the life, or a few days in the life of ICESat-2. And you can see the tracks laying down. Ultimately, you can imagine as it goes from pole to pole, ultimately those tracks are spaced pretty far apart at the equator, but they get really close together up at the pole. And you can start to see that evolving right now. You can see at the pole, there's that real dense area of green associated with where all those orbits are converging. That's really useful for us. In that one place on the globe, or actually two, because there's a mirror of it at the other pole, at that one place, there's actually a ton of data. You can see the green now. This is looking at the South Pole. That data dense region offers us a really good region to go and validate the measurements that are being made. We can go there, collect ground-based GPS data, and compare it to the satellite data to verify or make a verification of the satellite data that we're collecting. And that's what we decided to do. We said, hey, we can fly to Antarctica. You can do that. We can actually go to the South Pole. We can get in some tracked vehicles, and we can drive a section of that making ground-based measurements. And that's what we did. So in the next slide, this shows exactly how we got there. We flew commercially by aircraft to New Zealand. And then from New Zealand, we flew to the edge of the continent, a place called McMurdo Station in Antarctica. Then we flew into the South Pole. And then we got in these vehicles, which you'll see in the very next slide, which are really cool. But we got in these vehicles and we drove away from the pole. And we drove that triangle that you see in the upper right corner. That triangle is about 750 kilometers, or about 450 miles. I'm going to guess that that's probably Anchorage to Fairbanks, and then a little bit more distance-wise. Now, that doesn't seem like a lot, but we were doing it at about 12 kilometers per hour. So it took us 2 weeks to do that. In the lower right, you see the entire team. A team of 4 people. That's all it took. You see the entire team of people reflecting in the ceremonial South Pole. So the next slide is one of my favorite videos. This is how we did it. We basically have a piston bully. That's that tracked vehicle out front. That's what we're driving in. And it's dragging a 60-foot long sled. The sleds contained everything we needed to both survive and conduct the research. So in this particular sled, you see 3 sleeping tents. You see a generator, that big black box right in the middle. There's fuel drums that are right in front of the big black box, and there's all sorts of science gear kind of hanging off the back. This was a completely new plan for the United States Antarctic Program. This was an unbelievable idea that somebody came up with. I thought they were crazy. I did not think it would work to set up our tents once at the South Pole, then drive 750 kilometers and then take them down again. But it worked really, really well. No one was more surprised than me. So now we're going to give you a little point of view. I'm actually the person on the right in this video, and the mechanic, the most important person on the traverse, is on my left. Ultimately, this is our point of view sort of video of us driving. And in a second, so we've got a GPS set up on our vehicle, and we're going to cross the other vehicle's GPS, and we can basically then make a comparison of how those 2 ground-based measurements are being made. So GPS, you guys, your parents probably have a GPS in their car for navigation. Ultimately, that GPS that's in your car, or whatever you're using maybe to travel on the sea ice, that handheld unit or that thing in the car has about 3 to 5 meter accuracy. I bet those kids in the center frame there, I bet you guys are just a meter or so tall. So you don't have a great sense of spatial accuracy with the car's version of the GPS. With our GPS, when we process the data much later on, we can get down to centimeter level accuracy and centimeter level precision. So we know exactly where we are in space down to about that. More importantly, we also get the third component, the elevation component. So we make an elevation measurement using the highly precise, highly accurate GPS on the ground-based setup. And then we compare what we see on the ground to what we're getting from the satellite and make that validation and that verification that the satellites are getting the right elevation on our ice sheets. So this is the type of scenery that we see out there. It seems boring, but I think it's absolutely beautiful. But it's 2 weeks of that, so you got to like it a lot to enjoy it for 2 whole weeks. In the next frame, I'm sure you guys have seen something in the something similar to what's in the upper left. The sun dogs, those 2 little shiny spots on either side of the sun. The thing at the bottom is called a sun pillar, that shiny spot that looks like it's down at the surface. And then all those things together make up what they call the 23-degree halo. That is a result of blowing snow in the atmosphere and the sun bouncing off of that the way it does. I am quite confident that a lot of you guys have probably seen something similar to this in Fairbanks, but you really have to be, in Alaska, but you really have to be more in the polar regions to see something like this. In the lower left, that's a combination of a gas station plus our accommodations for the night. That's a major stop. And that image on the right is basically just giving you a sense of the wind. It's not overly windy in the center of the ice sheet, believe it or not, because this is the birthplace of the winds. But we had a pretty steady 5 to 15 knot wind, and you see those temperatures there. So Bonnie, you'd be very unhappy if you're not happy at 45 degrees. You're not going to be happy down there.
My reaction is brr.
And then this is just a whole bunch of different images of like around camp. In the upper left, that's our kitchen tent. It's very, very compact. Upper right, our whole group at the very end of the data traverse. The lower right is our refueling again at a gas station. And the lower left is, this is really at its heart a road trip, and that's you eat junk food, and that's what that is. That's beef jerky and maple syrup packs, all that good stuff. So Bonnie touched on the fact that we have a satellite, an airborne, and a ground-based component. We've just got one slide here associated with the airborne component. This is focusing on NASA's Operation Icebridge, which is a massive airborne campaign. And Icebridge is doing the same thing. From the air, they're shooting lasers down at the surface to get, again, an accurate and precise assessment of the elevation. And so we can couple the satellite data with the airborne data and the ground-based data to validate everything in one fell swoop. It's pretty cool. And these things are all happening pretty simultaneous with one another. The satellite is active right now. The Icebridge campaign that was down in this region just ended last week, and I'll be going down starting next week. So that's actually pretty close in time, especially given our interest in the center of the ice sheet, which is not changing all that fast. We can get away with a little bit of time difference. And here's the plane landing. And this is what it looks like, taking those 3 data streams and putting them all together. So this big circle out here, this is the aircraft, one of the laser altimeters on the aircraft. This little set of circles right here, that's the second laser altimeter that's on the aircraft. These guys right here, these dark green ones, that's the satellite track. And this black curvy thing, that's our driving. We're not as straight an arrow as either the aircraft or the satellite. And that takes us back to Bonnie's slide, which had the satellite, the airplane, and the ground-based stuff all kind of working in series with one another. Most of the times people think of NASA as a space agency, and that's totally fair, but we do a lot of just general Earth science with every tool at our resource, or at our disposal, and that includes the ground-based component of this. In this slide, I don't know if you can see it, but there's a couple of Twitter handles. One of them is NASA ICE, at NASA_ICE. That's a great handle to follow both the satellite and the airborne component. And then at near the sled down there, the SAD's ground-based sled, you can see my Twitter handle, which is Kelly M. Brunt. And that you can follow that. We'll be posting photos and whatnot for our upcoming campaign in Antarctica, which again starts next week or so. And that's all we had for slides. And I think at this point, Bonnie, I want to open it up to the classes for questions.
Yes. Whoops, I clicked on the wrong school. Thank you so much, Kelly. And Shishmaraf, do you want to ask anything before you have to go?
Yeah, we had 2 questions that came up in the presentation. RD, did you want to ask yours?
Where do you guys the data?
So the question is, when the satellite's collecting data, where does that data go to?
Yeah, so this is probably one of the greatest things about NASA. All of our data have to be freely available to the public as soon as it's, possible. In our case, we have to wait about 18 days to get the really precise GPS data to really know where we were. So there's a little bit of latency just on like pulling the lever and making stuff happen. But as quick as possible, we try to get it out to the masses. ICESat-2 data and IceBridge data are served via agency called the National Snow and Ice Data Center, NSIDC. But again, freely available to everybody. It doesn't matter where you are, US and international. Great question.
And the other question was, how many times does the satellite, it's a polar orbiting satellite, how many times does it orbit a day?
Yeah, that's a really good question. A little over 15. So 15 point something times a day. It goes around something like every 93 minutes. So if you do that math, you can figure it forward. We have 1,387 unique orbits that make up what we consider a full rev of our data. So we do that every 90 days or thereabouts, 91 days. So once we, you do 15 a day, you do 1,387 over the course of, say, 3 months, and then it starts to repeat. So it's flying. Most of the Earth-looking satellites, the ones that we put in what we call a near-Earth orbit, they move at about the same velocity. So they are all doing about 15, 16 orbits a day. Good question.
All right, thank you, Kelly. We're going to sign off. So
good luck with the volleyball.
Yeah, very much. All right, thank you for connecting, Shishmaraf. We'll say goodbye to you. I know you have to get off to volleyball competitions. Thank you for connecting. Yes, and keep measuring that permafrost. We're going to be able to compare those measurements, the changes in permafrost due to the thaw, with the elevations that ICESat's collecting as well. So thank you for connecting, and we'll come back over to Kelly. All right, and now we'll get some questions from the other schools. Let's see. Let's start over with Miss Picone's class. Do you have any questions for Kelly about the research or anything about how she got interested in science? It's open question time.
Awesome. Thank you so much.
Yes.
I have a question.
Tell us your name first. Please tell us your name first.
My name is Leo Alley, and this is a question for my friend Justin. What are your long-term expectations from the ICESat-2?
That's an awesome question. So there's a 2 on the end of it, right? ICESat-2. So that kind of suggests that there was maybe an ICESat, and there was. It was operational between 2003 and 2009. We just launched ICESat-2 in 2018. So there was a 9-year gap where we didn't have a satellite doing the same type of thing up in the air. And that's where IceBridge came in. We launched this big aircraft campaign in about 2009. It's still going on for about another year. But it was meant literally to bridge the gap. IceBridge, bridge the gap between the 2 satellites. Put all this stuff together, and what you end up with is an amazing, what we call a time series or data record of what's been happening in the polar regions. So we sort of have a first order sense of what we know is going on. And it goes back to those first slides I was showing you. There's a lot of loss in the ice sheets right around the fringe of Antarctica, right around the fringe of Greenland, where the ice sheets are in contact with the warming oceans and warming atmospheres. With ICESat-2, because we now have more than a 2-decade record of what's been going on, hopefully we'll not just know that things are changing, but we'll get a sense of the rate of change. Have those changes sped up? Is something stabilizing? We'll get a much better sense because we have such a longer and more complete sense of the story. So our initial expectations are we still expect to see those high rates of change along the perimeters of the ice sheet. And what we're excited to see is, what does the time series tell us as a whole? That's a great question.
Okay, thank you, Kelly. Let's go over to Crawford Elementary. Is there a question from Crawford? Oh, more than one.
Wow.
Excellent. All right, help me out, Ms. Trezino. Pick someone to come up, tell us your name, and ask your question. Adrian, I remember. Hi, Adrian.
I was wondering, how did you get that specific job?
Oh, so that's a great question. So I did my PhD studying what we call ice shelves. So we've got these ice sheets in Greenland and Antarctica. Around the fringe of Antarctica, there are these big protected bays. And some of the ice can actually come off the grounded bedrock, and in these protected bays, it can actually come afloat. So there are these areas in Antarctica where the ice is floating on the ocean. It's still attached to the ice sheet, but it's going up and down with the tides and doing all sorts of really cool stuff. I started looking at ice shelves using ICESat data. Remember the precursor, the satellite that was up between 2003 and 2009. And I did that as a research project, and then got so into it that I wanted to be a part of ICESat too. So that's how I came to NASA, slowly out of two research projects that I've been doing beforehand that got me using ICESat data. That's a great question.
So Kelly, I'm going to trace that back. So think about maybe science, when you have to do science research in the classroom, and maybe the science fair is coming, or you just have to do a research project. Those things that you're researching, look where the NASA connections are. Because Kelly shared previously when we were chatting that there's a website called the Science Visualization Studio, the SBS, and you might want to write that down in your notes for future reference. So when you're looking to study whatever you're studying having to do with earth science, check out what NASA has done and use that data. And, it could lead to something new to study, or a way to study it a little differently than what you may be thinking of. So thanks for that, Kelly.
And just to follow up on that for the teachers, I think every video that I used inside the presentation is available on that NASA SBS website. So there's so many great teaching resources in there as well.
Good point. Yeah, to be able to use in the classroom. Okay, I'm going to take one more question from Crawford before we move on, and we'll come back again. But I just want to go to everybody. So Ms. Trezino, help me out again.
Their arms just shoot up.
It's great. It's great.
My name is Jasmine, and how long have you been doing your job?
Oh, I've been here at NASA for 8 years. So when I came on, ICESat 2 was in development, a lot of planning still going on. Ultimately, so it was 8 years in the making to actually see it launch. That's kind of cool. The Antarctic side of things, as far as doing research in that area, I've been doing that since about 2000. So it goes back a few years.
Yeah. Let's see. I'm going to go over. I have not yet been to Chinook. So let me go up there to Chinook Montessori. Are there any questions up there?
Yes,
Anybody?
Bonnie. Yes,
Awesome.
we have two.
All right. Start with your name, please, so we know who you are. Hello.
Hi, my name is Eleanor, and I have a question.
Just answer this for you.
All right.
Why do you study ice?
I think ice is really interesting. I think what's kind of cool is I'm an earth scientist, and a lot of the things we study happen on long time scales. Think about some of the earth processes. Think about tectonics. You guys have a lot of earthquakes in Alaska. That's generally a very slow process. Think about the mountains around you and how long it took to build those. That's a slow process. Denali is still growing. That's a slow process. Ice is a lot faster. The processes involved with ice happen on much shorter time scales, and it's things that we can observe maybe inside my lifetime. I can see a lot of things change. So I think it's a combination of the skiing and then thinking about questions that I'll actually see evolve inside my lifetime, which is kind of cool.
And all of that skiing, I'm guessing, I do a little bit of skiing myself, but all of that skiing would involve a little bit of ice.
Yeah.
Probably not the best part of skiing, right? Yeah. So whatever you're interested in, I think that was a great question, because why ice? That's what got you interested. So, you know, yeah. So whatever it is that you're doing, be curious about what's around you, because that's what you'll really have a passion to study. So great question. Thank you for that. All right, let's go back. I believe that Mr. West said there were 2 questions there. So let's get another one while we're there.
Hello, my name is Mark from Archie's class. My name is Mark from Archie's class, and my question is, what do you guys do with the ice?
What do we do with the ice? So on this particular project, we're not collecting any ice in the field. We might do a little bit of sampling of the surface while we're out there, just looking at snow density, but we are not collecting ice on this mission. I've been on other missions where you do collect ice, you drill cores. Sometimes people like to drill long cores and get a sense of what's happening to the ice sheet, you know, through a lot of depth. And they'll sample these things, and those cores become very valuable. They were expensive to collect. You want to sort of hold on to them. Somebody might do other science with that ice. There's actually a giant freezer in Denver where we store all the ice so that other people have access to it down the road if they want it. And it's called the National Ice Core Laboratory, and it's a freezer the size of the building behind Bonnie. It's an absolutely immense building that houses big freezers, minus 70-degree freezers, minus 40-degree freezers. So there's a repository, or kind of a library, for ice cores once they're collected. We won't be doing that. We've got an easy gig here. All we do is collect GPS data. It's super simple. Don't tell anybody. It's super easy.
Thanks. That was a great question. I'm going to show you the building behind me again, just so you can get that image. That was a great comparison, Kelly. And I had a question that came to mind as I was listening to you and thinking of the question of why ice. If I was interested in ice, where else besides Earth could I study ice?
There's a couple of smaller bodies that orbit places like Saturn and Jupiter, and we have found over time, as our ability to look out in that direction gets easier and easier, and looking at small objects becomes easier and easier, we have found these icy bodies. They include Europa. It's my understanding that NASA is planning quite a few years from now to go back to Europa, and that's pretty exciting for an ice researcher. And Europa is a pretty good size. There's a small body, and this is why I was really emphasizing, it's taken us time to get to the point where we can look at smaller bodies, but there's this tiny thing called Enceladus, which is about the size of like the United Kingdom or Great Britain. That's not very big at all, and yet we still know that that's an icy body as well. So there are certainly other bodies out there that have ice, not quite like ours, usually a lot colder. So they're a lot harder. The ice there is actually really, really strong. You can imagine like maple syrup. If you make maple syrup cold, it doesn't flow very fast, but if you heat it up, it flows a lot faster. Our ice here on Earth flows a lot faster than some of these other bodies. They're a bit colder, and they just don't flow as fast. It's cold maple syrup.
Great analogy. Very cool. Okay, let's go back over to MT Scott. I see is that a hand up? Or are there any other questions there?
We do have a few more questions.
Okay.
Hi, my name is Ashton, and our class has 3 questions.
Okay, thanks, Ashton.
The first one is from Amanda, and it says, how is a satellite able to move so fast?
Oh man, these are just, okay, so you're talking to a glaciologist, but this is orbital mechanics. If we put something out a little bit farther, it would take a little bit longer for it to whip around. So it basically just has to do with the altitude that you've put it up in. because we have the ability to move it around inside the orbit, but we don't use thrust or anything like that to anything with respect to speed. It's just orbital mechanics. And I think some of that is also tied up with the inclination. Are we equator sort of revolving, or we go the pole? So a lot of it's tied up with orbital mechanics. Sorry, I'm a glaciologist.
No, that's very good. And it has to do, that's a great question too.
Yes.
So there are satellites at very different places, and you'll find, here's a research question. It's okay to say, I don't know. We don't need to know everything, but we need to be curious and look it up. So that's a great question. So I would suggest go and look at some other satellites. Here's trivia. What's the only satellite that humans have lived on for almost going on 20 years now? Any guesses? Anybody? It's a satellite orbiting Earth. I'm going to go from classroom to classroom and see if there's any guesses.
Hold on.
The International Space Station.
Oh, where was it? I missed it. Whose class was that? Ah, here I go. Say it again, please.
The International Space Station.
Woohoo! That's right. Tell me your name.
Lance.
Hi, Lance. You're exactly right. Astronauts have lived for 6 months at a time. A couple of astronauts were there for a year, but they've been living on the International Space Station for almost 20 years now. We've had astronauts living up there. So that travels at a very specific speed to keep it in orbit, in the specific orbit that it's in around the Earth. And orbital mechanics is a great field to study to understand that better. So there were more questions. I'm going to come back over to Mount Scott. You said there were a couple more questions. Go ahead.
Yeah. And Bonnie, unfortunately, we do have to jump off the call at 2:45 because we have a passing period.
Okay. So just a couple more minutes of connection then, right?
Yeah.
Okay.
Okay. Then, what is the most difficult part of the job?
Typical day in the life of Kelly Brunt.
There's a lot of problem solving when you're out in the field, or even when you're at your desk, maybe generating code for some of these projects. And while those are challenging, I think that the people that get into science and get into this type of field, they actually like those challenges. So even though it's challenging or difficult, I think that that's one of the things that we like about it. That's about it. Sometimes the math gets hard, I'm not going to lie, but math is a muscle, so keep working it, kids.
Good advice. That's really good advice. Yeah, math is a muscle.
And I think Ashley had one more question for us.
Yeah.
Hold on, you're muted.
Oh, you're breaking up a little bit. Just start over.
I think they're muted now.
What inspired you to do this job?
Yeah, I think it was just working with ICE and being a part of the Antarctic program for a number of years. It's a really unique opportunity, and you get a sense of that when you talk to people and you see their interest in it. I think the interest in the field and the skiing background, I think those are the two biggest contributors for sure.
Right. Yeah. Awesome.
Thank you so much, Kelly.
Thank you.
Thank you, Oregon.
All right. Thank you. We'll say goodbye to Mount Crawford. I appreciate you connecting. They were great questions. Thanks for being with us, and follow Kelly on Twitter. Okay. So I'm going to come back over to, where are we? Let's see. Crawford Elementary. All right. And we'll come back to you again. Chinook, I just went over here to Crawford first. All right. Help me out with picking someone, Ms. Trezino. Hi again, Lance.
This isn't really a research question. It's just a question for people to get to know Kelly some more.
Okay.
Did you like it down in Antarctica? Did you prefer it down in Antarctica more than you did up here in Alaska?
Okay, so that's a great question. Here's the key to living in Alaska or living in Antarctica or living in Maryland. I think you have to appreciate what your area has to offer while you're there. So when I'm in Antarctica, one of the things I really like is that I'm not sitting in DC area traffic. My commute is easy, right? That's fantastic. Oftentimes somebody else is making our meals for us, like when we're on station. It's an easy life. You know, it's very, and it's amazing scenery. It's absolutely gorgeous. What you don't have access to, or you can't run out and get Chinese food, or you can't go to a movie or something like that, but that's okay because everything that you have while you're there is amazing. In Alaska, what I really liked there was look at how big that state is and how many places you can go that are just so different from one another. Think of the wildlife you have there that you see on a daily basis, nearly a daily. I mean, you guys probably see a moose once every 3 days, right? That doesn't happen in Maryland. That's pretty cool. So you just have to appreciate what your area has to offer and not miss the stuff that the other places have when you're not there. Alaska, Antarctica, you know, they're both amazing and special places.
Thanks, Kelly. Great question. Okay, was there another question that someone would like to ask while we're here? Come on up.
Yeah, we've got one more. Sage is going to ask a question.
Okay.
Hello.
How's it going?
My name is Sage. How long do you get the data? How long does it take to get the data from the satellite to Earth?
Oh, that's a great question. First of all, I just want to say one thing about your classroom. I love what every time you guys are asked if there's a question, like all these arms shoot up straight as an arrow. It's fantastic to see your enthusiasm. The data, we can downlink the data 2 to 3 times an orbit. I think our plan right now, you know, we haven't had any data volume issues. I think our plan right now is we're downlinking either once or twice. I can't quite remember. I apologize. So you can collect the data and the satellite's going around the globe once every 93 minutes. So we're downlinking the data once or twice every 90 minutes. That's the first step. You get it down to the ground. Now you got to pipe it over to Goddard where we're actually, you know, pulling the levers to process these data. We're looking for real accurate and real precise measurements. So we have to let some time evolve so that we understand exactly where our GPS satellites were when that measurement was made. And we have to wait about 3 weeks to do that. So now you've downloaded once or twice every 90 minutes. You've piped it over to Goddard. Then you've waited the sort of 3 weeks or so. And then we, you know, eventually when we get out of what we call our commissioning phase, eventually we'll be getting data to people in that sort of month type time frame. So 1 month from data collection, we'll be able to not only have it on our desktops, but put it on everybody's desktop. Doesn't matter where you're from, US or the international community. So I think that gets at your question. That was a good one.
Great. Okay, I'm going to go back over to Chinook Montessori. Is there another question there? I see one hand up.
My name is Trenton, and my question is, what temperature was the water in Antarctica?
Oh, okay. So keep in mind that the surface of the ocean is frozen, right? Or sometimes frozen. When I was down there, there would be a thin layer of sea ice on the ocean, right out in front of base. It's salt water, so it can actually get a little bit colder in temperature before freezing. So it's going to be a few degrees below zero. I want to say like -4 is generally what the water, -4 Celsius, I'm sorry. I think that's what the temperature of the water was right outside of station. And that keeps kind of maybe some sea ice, but the whole thing wasn't solid. So, so you want to be, pretty close to freezing. It was chilly. It was, I'm not going to lie, a couple of us jumped in and then jumped right back out, but it's cold, but it's not completely unbearable.
Oh, that's the ultimate polar plunge, Kelly.
It's pretty cool.
Okay, I saw someone in the back. You have a long sleeve white shirt on. Come on up. Yep, I see your hand up. Come on.
There we go. Say your name first.
Hi, my name is Neva, and why were you interested in becoming a scientist?
I think that's a really good question. I think
great question.
I'm not gonna lie. Like when I was in high school, math was fine, but I didn't always enjoy it. But I slogged through with it. I did like the sciences. I like when you can sort of ask a question and try to get at the answer. And I did eventually appreciate that math was part of the tool to help you get at some of those answers. So I think as you guys go through school, there might be something that you don't always like, but it's part of what you want to do. I encourage you to sort of stick with it a little bit. You don't have to be the best at it for sure, but try to do your best to keep these tools and move forward. They might come in very handy in your future. So I think it was, getting into the sciences mostly because of the sort of answering of questions and being able to do it on your own. Not necessarily, it's great to be able to Google things when you want to know something, but it's also nice to, every once in a while, I'll Google something, and unfortunately, the answer to that, maybe somebody on my hall, I end up accidentally Googling people I know to get at the answers. It's nice when you're part of the answering part of the community.
Right. Yeah. Right. So being curious and wanting to understand better and then being able to look for those answers yourself is a great, that got you interested in science. Neat. Yeah. So I'll come back for one or two more questions to Crawford Elementary, but I want to first ask a question. I mentioned there'd be a quiz at the end. So Kelly mentioned going to Google to look things up, and we've talked a lot about different data collection. What does it mean to verify data? What does that mean? And I'm going to come over to Crawford first. You don't have to have the answer, but do you have any guesses? What does that word verify mean? How do you verify? What have we been talking about here? Go ahead. I'm glad you're running the classroom, Miss Trezino. Thank you. Go ahead.
Just tell them your name and then what you think
Okay,
verify.
my name's Christopher. I think verify means like double checking it to make sure it's right, sort of.
I like it. Yes. So what's the double check that you've been doing, Kelly? What's the double check?
We've been basically looking at the satellite data and double checking it against our ground-based data. So that's the verification or the validation.
Right. Excellent. Yes. So I want to share with you, are we ready to do that? Okay. I want to share with you a way that you all can be involved in this verification process. There is currently a Globe campaign. Here we go. There's currently a Globe campaign running where your measurements of trees, it's called Trees Around the Globe, and it's a mathematical process. So I know you all love math. Kelly talked about that. You don't have to be great at math, but math is a tool you will need to be able to study science. So it helps you get better at math, and it helps you participate in this ground measurement campaign. You're going to measure the trees for this campaign, the trees around your school, around your location. Submit that to the Globe website, which I know your teachers know how to do because they participated in the training up at University of Alaska as part of Arctic and Earth Science. And that data will be used by the ICESat scientists to verify elevation, because the elevation of the trees, as you saw in the video, where the photons were coming down and bouncing off the trees, is one of the points that are being measured. So I want to share that with you and make sure you're aware of that campaign, because it's a great way to be able to participate in that ground truthing. Let's see. I think I'll stop with that now because I want to get to your questions are so good. I want to share with the teachers a way they can become involved through a program called Polar Trek. So I'll just mention that here and plant that seed. Kelly shared that with me, but we'll send that out to you after the broadcast, I think, rather than going into it here, because I really am enjoying the questions from the students. But Google Polar Trek, teachers, if that interests you. Okay, where were we? I think we're going to come back here because I asked you questions, but I want you to be able to. So go ahead, Ms. Trezino, give us another person.
There you go.
Hi, my name is Isabella. I was wondering, what is so fun about your job?
Oh my gosh, almost all of it. I think, so in the work I've done, my job has taken me to 5 out of the 7 continents, and that's amazing. So getting into the sciences is first of all a really, really good way to see the world and get a sense of what's going on in the world around you, and that's been amazing. We go to super interesting places. A friend of mine was talking about how when he sits down on an airplane, if somebody asks him what he does for a living, he has to just fold up his book and put it away, because they're going to keep asking him questions. I think people are really interested in the polar regions, and they're really interested in talking directly to the folks that have a sense of what's going on today. And that's been pretty cool to not only like what I do, but be able to communicate it to other people because they're interested in what you do. Not every field is like that. There are a lot of fields that you sit on a plane, you don't want to hear about the other fields. So I think it's getting to see a lot of places and being able to communicate that back to an interested group of listeners. That's been pretty amazing.
Yeah, and we thank you for doing that. Whoops, let me switch over to me. We thank you for doing that with us here today, Kelly. It's been great to hear all of the information that you've shared and be able to learn more about what you're doing. And I look forward to following you as you head off for travel next week. Yeah.
Yeah.
So we have like 2 minutes. Are there any other burning questions at each location? I hesitate as I ask that because there'll be 10 and we just can't stay connected forever. But I'm going to go to one school, and if you want to pick one more student, we'll close with that. All right. We're over on Chinook now. Go ahead. I think you're still muted. There you go.
And have you ever researched anything besides ice?
Yeah. So I was pretty interested when I was getting my master's, believe it or not, in the magnetic field around the planet. So I did some work looking at magnetism in rocks. Not as interesting as ice. It's good, but it's not as interesting. Great question. Thank you.
The magnetic field's pretty cool. That's why we have the auroras, right? So that's pretty cool.
Right.
Yeah.
That's
yeah.
right.
Good. All right. So back over then to Crawford Elementary. I know it's hard to pick, but is there one more person? There we go.
There he is.
Okay, go ahead.
Hello, my name is Nolan. And what will be the biggest impacts on the ice melting for us in Alaska?
Okay, that's a great question. So let's talk about ice sheets. Help me out. You guys are in Chinook Middle School. So are you guys local to Fairbanks? Is that right? Where's that school from?
Yeah, we're just south of Fairbanks.
Oh, you guys are Allison Air Force Base. Yeah. Okay. So the biggest impact on you guys is not necessarily ice sheets where the water is melting into the ocean and raising sea level. You guys are more concerned about sea ice. As we lose sea ice, if you remove the cap on the ocean, you basically change the heat exchange between the ocean and the atmosphere, and that's the one that has the global impact on weather. So that definitely affects you guys in Fairbanks, even though you're in the center of the state. You guys are so remote and isolated in the center of the state, but changing sea ice has an impact on your weather. So the school, the other school, the elementary school, where are they from again? I've totally forgotten. I'm sorry.
Okay, so the other school that we have is Crawford Elementary. Oh, no, that was Crawford. Excuse me. It's Chinook Montessori.
And where are those guys? Are these coastal? I forgot. But you can see that coastal communities are affected more by changes in our ice sheets. Inland communities, like the Eielson Air Force Base area, they're more affected by changes in our sea ice.
Right. Mr. Fontes, can you help us with that? Where are you?
I'm so sorry.
No, I did too. I apologize myself. Yeah.
We're actually right in Fairbanks.
Oh, so
Okay.
yeah, you're going the same situation. The impact for you guys is mostly on the sea ice change.
Right. I remember that. Well, and I also remember that, and I know I say it often, so if I already said it once, what happens in Alaska doesn't stay in Alaska because there are global wind belts that are affected by changes in Alaska. If it wasn't hot at the equator and cold at the poles, some of the wind belts traveling around the earth would not be traveling in that way. And so as that changes, as the pole is not as cold as it used to be, that affects all of us.
That's right. That's right.
Yeah. So, all right, we'll wave to you. First, we'll wave to Chinook Montessori. Thank you for connecting. It's been wonderful to have you with us today. Thank you. And to Crawford Elementary, thank you so much. It's been wonderful to have you with us. Both schools had fantastic questions. And Kelly, thank you so much. I look forward to following you. Stay warm. Enjoy your snacks.
Thank you very much.
Maybe we'll touch base with you afterwards.
Thanks for everybody's interest.
Yes, thanks so much. All right. Bye-bye, everyone.
Oh, man.